All right, so perhaps the easiest way to uh, get a state space model is to start from the Laplace domain or the transfer function representation. And the way I'm going to show that is by looking at this example with a circuit. So what we can do is when we write KVL, we can do so using the Laplace transform version. So we want to write KVL using Laplace. And so starting here, we're going to get VI of S is equal to R times I of S plus SL I of S plus 1 over SC I of S. All right, so that would be one equation. All right, the second equation would be that 1 over SC times I of S is equal to V out of S. And we can just sub this directly. So sub 2 into 1. And what we get then is the following. We're going to get S squared times L times C Okay, so as an aside, if you're confused on the solving step here, all I did is I said that I of S is equal to SC V naught of S. Okay, so now we have S squared LC V naught plus SRC V naught plus V naught is equal to VI. Okay, and then what we can do is take the inverse Laplace transform. And what we'll do is we'll say y is equal to v out and r is equal to v in. Okay, so let's take the inverse Laplace transform. And what we'll get is y double dot LC plus y dot RC plus y is equal to r. And then what we want to do is the really key step, and that's to assign states. So assign states in the following way. X1 is equal to y, x2 is equal to y dot, which means that x1 dot is equal to x2. All right, and of course that also means that x2 dot is equal to y double dot. And so what we want to do is look at this particular equation right here and then look at the equation that's here. And I want to solve that upper equation for y double dot. So we'll solve for y double dot. And what we'll get is that y double dot is equal to minus r over L y dot minus 1 over LC times y plus 1 over LC times r. Okay, so then let's replace with the state representation. So we'll just replace this with the states. And what we'll get then is that we have x2 dot is equal to minus r over L x2 minus 1 over LC x1 plus 1 over LC times r. Okay, so what we can do is collect these into matrices. And so we would get x1 dot, x2 dot is equal to the following. So x1 dot is equal to 0x1 plus 1x2. So x1, x2 is here, plus 0 times r. All right, x2 dot is equal to minus 1 over LC times x1. So that's minus 1 over LC times x1 minus r over L times x2 and plus 1 over LC times r. All right, and then the last thing I need is my output equation. All right, output. So y, which is my output, I've already defined in terms of states. In fact, it's just right here. It says that x1 is equal to y, so that means y is equal to 1, 0, x1, x2. All right, what that means is that y is equal to 1x1 plus 0x2 plus 0 times r. All right, and altogether, that gives me my solution. And we can double check. In this case, the order of the system is 2. So n is equal to 2. All right, m is equal to 1. There's only one input, r. And q, my number of outputs, is equal to 1. So we have then n is equal, so this should be 2 by 2, which it is. This should be 2 by 1. This should be 1 by 2. This should be 2 by 1. And this should be 1 by 1. All right, so again, everything makes sense as far as dimensions go. So we are as happy as can be. So that constitutes the whole solution to this particular example.